In the competitive world of commercial aviation, one thing determines who stays ahead: the engine. For decades, aircraft manufacturers have relied on engine upgrades to keep old designs alive. Boeing's 737NG and MAX series. They've stretched the lifespan of that model to over 57 years. Airbus SA Senarling Neo Ceres. It revolutionized efficiency with modernized engines. Some of these engines were so advanced they earned Guinness World Records. But here's the truth: breaking records doesn't always mean changing history. Yet today, a few new engines actually might. They're redefining how the future of flight looks and how sustainable it can be. Welcome to Flavia. In this episode, we'll explore two revolutionary engines reshaping the aviation world: the CFM Rise and the Rolls-Royce. We'll uncover how they're built, why they matter, and how they could change aviation forever. Before we take off, make sure to subscribe so you don't miss the future of flight. Alright, let's dive in. Our story begins with the CFM Rise, a groundbreaking project born from a collaboration between Safran Aircraft Engines of France and GE Aerospace. Launched in June 2021, this program aims to develop an engine that runs on sustainable aviation fuels and hydrogen, targeting 20% lower CO emissions and fuel burn. To understand why this is a big deal, let's rewind a bit. Jet engines have evolved from simple early designs into today's complex turbofan engines, which use high bypass ratios for maximum performance. But chasing efficiency often meant bigger, heavier engines. So engineers began exploring an idea that once seemed impossible: open rotor engines, or unducted fans. These designs move massive amounts of air more efficiently than traditional TURB, OFANS. Companies like Pratt & Whitney and General Electric experimented with this concept. The 578DX and GE36 were both promising, but they faced big challenges: noise, vibration, and complexity. The technology simply wasn't ready. Fast forward to today, and everything's changed, thanks to breakthroughs in materials, aerodynamics, and computational design. The CFM Rise has turned what was once a dream into reality. Safran and GE have developed an open rotor engine that's as quiet as today's modern turbofans, a huge achievement. Its latest prototype looks similar to the old GE36, but there's one major difference. It uses gearbox-controlled, counter-rotating fans, which drastically cut noise. GE later refined the design into a single fan system with adjustable stator vanes to better control airflow and further reduce noise. This isn't just an aesthetic change, it's a mechanical revolution. By simplifying the gearbox and optimizing the flow, CFM has made an open rotor engine that's efficient, quiet, and easier to maintain. The Rise features a 13-foot rotor diameter, far larger than most engines. Its compact core and energy-recovering recuperators reclaim lost exhaust heat. And here's where it gets even more futuristic: carbon fiber composite blades, made using a new 3-axle weaving technique, ceramic matrix composites in the hot section for heat resistance, and an integrated hybrid electric system designed to cut fuel burn by 20%. It's not just an engine, it's a statement about the future of sustainable aviation. Next up, Rolls-Royce's UltraFan, a project that could define the next generation of jet propulsion. Unveiled in 2014, the UltraFan was initially a testbed, a playground for new ideas. But by 2023, it became reality, undergoing testing at Testbed 80, the world's largest jet engine test facility running entirely on 100% sustainable fuel. Rolls-Royce CEO called it a transformative technology, and he's not exaggerating. The UltraFan has a massive 140-inch fan diameter, making it the largest jet engine ever built, even bigger than GE's record-setting GE9X. It boasts a bypass ratio of 15:1, meaning it pushes an enormous amount of air, quietly and efficiently. Its gearbox system lets the fan and core spin at different speeds, maximizing efficiency, achieving an aerospace power record of 64 megawatts during testing. The carbon titanium fan blades are lighter and stronger than metal, resisting corrosion and fatigue while improving performance. A line-burn combustor ensures lower emissions and cleaner operation. The UltraFan isn't just massive, it's efficient, 25% more efficient than the first Trent engine, up to 20% less fuel burn per flight, 40% fewer nitrogen oxide emissions, 35% quieter than older models. It can deliver anywhere from 25,000 to over 100,000 pounds of thrust, making it suitable for both narrow and wide-body aircraft. And just like the Rise, it's future-proof, fully compatible with 100% sustainable aviation fuel. Designing a jet engine for an aircraft weighing over 200 tons isn't easy. Every step must be approved and tested before assembly even begins. Take the Rolls-Royce Trent XWB, for example, designed in 2004 for Airbus's A350. It took 6 years from concept to flight. At Rolls-Royce's Derby facility, a new $35 million engine rolls off the line every 20 days. Each fan blade is precision crafted, honed like a knife, and installed by hand. Every component, over 20,000 parts, must fit perfectly. And before shipment, each engine faces extreme tests: fan blade off containment, water ingestion, bird strike, cold start. Only after passing all these does it earn the right to power an aircraft. In 2023, the global aircraft engine market was valued at $95 billion. Over the next decade, it's expected to hit $187 billion, growing nearly 8% annually. Here's who's leading the race: CFM International, 39%; Pratt & Whitney, 26%; Rolls-Royce, 18%; GE Aviation, 16%. But that balance might be shifting. Rolls-Royce's UltraFan is 5% larger than JS GE9X and could soon take the title of the largest and most efficient jet engine in the world. However, GE still holds the record for the most powerful engine ever built. With the GE9X generating 134,000 pounds of thrust, the question now is, will Rolls-Royce's UltraFan break that record? Or will GE's dominance continue? So, if you were an aircraft manufacturer, which engine would you choose? The CFM Rise, leading the charge toward hydrogen and hybrid electric aviation, or the Rolls-Royce UltraFan, the most advanced and efficient giant ever built? Let us know your thoughts in the comments below. And if you enjoyed this look inside the future of flight, like, share, and subscribe, because the next generation of aviation is just getting started. When you look at a modern jet engine, what you see on the outside is only a fraction of what's happening inside. Every rotation of those blades, every burst of heat and thrust, it's the result of tens of thousands of synchronized components working in perfect harmony. Inside the core, air is compressed to 50 times the pressure of Earth's atmosphere, then ignited in a controlled explosion that propels the aircraft forward at nearly the speed of sound. But making all of this happen again and again, without failure for years, is a feat of engineering unlike anything else on Earth. Each component, from turbine blades to the tiniest sensors, must survive temperatures over 500 degrees Celsius, endure extreme vibration, and perform flawlessly at 35,000 feet, where the air is thinner than anywhere on the planet. Now imagine scaling that performance up and making it 20% more efficient, quieter, and sustainable. That's what engines like the Rise and UltraFan are doing, rewriting the physics of flight. The aviation industry contributes around 2.5% of global CO emissions. It might sound small, but in an industry this massive, that's hundreds of millions of tons of carbon every year. With global passenger traffic expected to double by 2040, efficiency isn't optional anymore. It's survival. Airlines know it. Manufacturers know it. And that's why the push towards sustainable aviation has become the next big race. The CFM Rise represents that transition, an engine that could eventually run on 100% hydrogen, emitting zero CO during flight. Meanwhile, Rolls-Royce's UltraFan is paving the way for engines that are ready for net zero. Aviation fuel right now, these aren't just machines. They're symbols of how far human innovation can go when survival and ambition meet. But here's something most people don't realize. Before an engine ever touches the wing of an aircraft, it goes through some of the harshest tests imaginable at GE's testing site in Peebles, Ohio. Engines are strapped down in massive concrete chambers where they face hurricane-force winds, sandstorms, and freezing temperatures as low as -40 degrees Celsius. At Rolls-Royce's testbed, the UltraFan is subjected to 64 megawatts of simulated flight power, pushing the limits of what's possible for any gas turbine on Earth. Engineers run tests where birds, ice, and gallons of water are fired into spinning fans to ensure they can survive real-world disasters. It's brutal, but necessary. Because when a $350 million aircraft is flying at 900 kilometers per hour with hundreds of lives on board, there's no room for almost. You might not think much about noise when you see an airplane, but for engine designers, silence is a science. Older open-rotor concepts failed largely because of noise. Those exposed blades created ear-splitting turbulence. But with modern blade geometry, composite materials, and gearbox-driven rotation, the Rise engine has achieved near turbofan-level quietness. That's not just for passenger comfort. It's critical for airport regulations and nighttime operations. Every decibel saved is another step toward a greener, more acceptable form of aviation. In the competitive landscape of commercial aviation, the engine has been a pivotal factor, with manufacturers updating engines to keep older aircraft designs viable. Notably, Boeing's 737 nanograms and MAX series have extended the model's lifespan to over 57 years, and Airbus's Neo series has achieved success by modernizing engines for enhanced efficiency. The ingenuity of some engines is such that they have been recognized with Guinness World Records, yet achieving a world record does not. Assured that an engine will be enough to make a transformation in the history of aviation, but with nowadays development, there are actually such engines. Find out in this episode of Flavia. What are these engines? How are they made? And why are they changing the industry? But before we start, please hit the subscribe button if you haven't already, so you'll be the first to see our next videos. Now let's dive in. The first to mention should be the CFM Rise revolutionary innovation for sustainable engines. This initiative is a collaborative venture between Safran, Aircraft Engines of France, and GE Aerospace. The project was launched by CFM in June 2021. And the goal of the partnership is to develop an engine compatible with sustainable aviation fuels and hydrogen, aiming to decrease CO2 emissions and fuel usage by 20%. To understand the importance of the CFM Rise engine, it's crucial to briefly review the evolution of aircraft engines. Jet engines have undergone a remarkable transformation, from their simple beginnings to the advanced turbofan engines of today, which boast high bypass ratios for enhanced performance. However, the quest for efficiency has led to heavier engines due to increased fan diameters. To address this, the industry has explored alternative designs like unducted fan engines, which efficiently move larger air masses. Historical attempts at such designs, like the Pratt & Whitney Allison 578 Delta X-ray and the General Electric G36, showcase the potential for fuel savings and operational efficiency despite their innovative features. These engines were not pursued further due to challenges such as noise levels and mechanical complexities. But fortunately, despite the setbacks faced in the past, the aviation industry has seen a resurgence of interest in open-rotor engines, thanks to the latest breakthroughs in material science, design techniques, and computational advancements. These developments have made the CFM Rise engine not just a possibility, but a highly sought-after innovation. Safran has taken the lead in this revival, successfully developing an open-rotor engine that matches the quietness of modern turbofans. A remarkable achievement. The engine, tested extensively in 2017 and 2019, mirrors the G36 unducted fan in appearance, but stands apart with its gearbox-controlled counter-rotating fans, achieving noise levels comparable to the latest CFM LEAP engines. Additionally, in a collaborative effort, General Electric has refined the design, further transitioning to a single fan system with adjustable stator vanes for enhanced airflow management. This streamlined gearbox design, reminiscent of those in turboprop engines, not only simplifies the engine's mechanics, but also holds the promise of additional noise reduction. Marking a pivotal development in the CFM Rise engine's journey, the CFM Rise stands out with its 13 feet rotor diameter, setting it apart from its predecessors and other traditional turboprops. Its core is more compact compared to the G36. The design incorporates recuperators to reclaim energy lost through exhaust heat. While it may resemble a conventional counter-rotating engine, it differs in that the second-stage blades are stationary and the stators have an agave pitch for adjustable control. These components serve as flow recovery vanes, enhancing the fan pressure ratio and managing rotor loader reduction. Gearset links the turbine and rotor. CFM will employ a 3-axle weaving technique to create the carbon fiber composite blades for these engines. The engine's hot section will feature ceramic matrix composites and advanced metal alloys by integrating a hybrid electric system. The engine is poised to cut fuel consumption by 20%, marking a significant advancement in aviation technology. The second one is the Ultra Fan of Rolls-Royce. It was unveiled in 2014 and initially served as a new engine concept and a testbed for new technologies due to low interest in large gas turbines from aircraft manufacturers. Testing began in early 2023 at Testbed 80, the world's largest aero engine testing facility, using 100% sustainable aviation fuel. Rolls-Royce CEO Tufan Ergin-Bilgic described the Ultrafan demonstrator as a transformative technology for both current and future engines. Notably, the Ultrafan has a massive 140 in diameter, making it the largest jet engine, surpassing the GE9X, is 135 in the Ultrafan design, focuses on improving efficiency, reducing emissions, and enhancing performance. It features a high bypass ratio of approximately 15:1, achieved through a large fan and a relatively small core design. This high bypass ratio results in a quieter and more efficient engine. Additionally, the Ultrafan includes a power gearbox that allows the fan to rotate at an optimal speed, different from the core, delivering an aerospace power record of 64 megawatts during testing. Carbon titanium fan blades, stronger and lighter than traditional metal. Blades further improve performance by withstanding high loads and temperatures while resisting corrosion and fatigue. The lean burn combustor also contributes to lower fuel consumption and emissions. The Ultrafan offers substantial benefits in terms of sustainability and adaptability. It is 25% more efficient than the first generation Trent engine, potentially saving up to 20% of fuel per flight compared to current engines. Emissions reductions include nearly 40% less nitrogen oxide and 35% less noise than Trent engines, with virtually no non-volatile particulate matter. With a thrust range from 25,000 to over 100,000 pounds, the Ultrafan can power a wide variety of aircraft, making it particularly significant for Rolls-Royce as they aim to strengthen their position in the narrow body market. The Ultrafan F future-proof design, capable of operating on 100% sustainable aviation fuel, ensures its relevance and superiority over other market-leading engines like the GA9XPW1100 GJM and LEAP-1A SO. How are these engines designed when it comes to crafting engines for colossal aircraft weighing 200 tons? The design process is intricate and must receive official approval prior to assembly. Engineering teams within companies are extensive, tasked with meeting the detailed demands of their clients, making this the most costly and time-intensive stage in engine creation. The Rolls-Royce Trent XWB engine, for example, underwent a 6-year design and construction phase initiated in 2004, when Airbus sought a new engine for the A350 by 2006. Rolls-Royce was selected to fulfill this need, and in 2010, the A350, powered by 2 Trent XWB engines, took flight. Rolls-Royce's Derby facility in the UK is a hub for jet engine assembly, where the complex process is routine for the workforce here. A new $35 million engine is produced every 20 days. Starting with the fan disc, a robust component that secures all 22 blades each, is finely honed as a chef's knife for efficient air movement. Expert workers install these prefabricated blades and insert annulus fillers between them to optimize air flow, completing the fan assembly, a key part of the XWB. The engine's fan is positioned at the front with the turbine and shaft at the rear, driving the fan. The low press turbine is vertically mounted at the engine's rear, and the core is constructed piece by piece. Concurrently, the fan is moved to another area for casing assembly, a detailed task involving numerous wires and pipes. As the core is completed, it's aligned with the fan and case, ensuring a perfect fit. As this occurs, another group finalizes the core assembly, starting from the compressor and working upwards to the combustor and turbines. They have to work fast because the assembly floor moves up as the engine comes together. After the engine core is fully put together, it's time to attach it to the fan, and its housing. The core is laid out flat, and a rotating mechanism ensures that the fan blades fit snugly into their housing. Behind the massive fan, 68 turbine blades work together, each with a power of 4 cars, cumulatively. surpassing the output of 300 cars, although it takes 20 days to assemble the engine. It's not ready for shipment until it passes rigorous testing. Rolls-Royce conducts these tests in a special control room where the engine is tested on a rig and the operator acts as a pilot, but only after all safety locks are engaged to prevent entry during operation. Each test is meticulously recorded to confirm the engine meets every customer specification. The testing area is designed to isolate noise, allowing the control room to remain quiet. There are three main types of tests: pass-off tests to verify performance standards, research tests and development tests where the most intense evaluations occur. These include a fan blade-off test to check containment, water ingestion tests to simulate heavy rainbird, strike tests, and cold start tests to assess performance in freezing conditions. Once the engine clears all tests, it's ready to be shipped, usually on a flatbed trailer, but sometimes by cargo ship or even an aircraft like the Airbus Beluga for urgent deliveries at the assembly facility, such as the one in 2 for the Airbus A350. The engines are mounted onto the aircraft at one of the final assembly stations. Rolls-Royce and Airbus have a long-standing partnership ensuring the delivery of these efficient engines. The Trent XWB engines, weighing 8 tons and costing $32 million, each are carefully lifted by a hydraulic crane for mounting precision, is key, as nearly 20 parts are assembled by hand and any error could be costly. The engine is